Okay, so I'd like to pick up with vectors as to where we left off in class and just look at a couple things. So let's say that I wanted to add vector A to vector B. And here is the wonderful thing about vectors, is that this vector A can be moved around anywhere at all, and it's still vector A. As long as the magnitude or the length and the direction stays the same, then this is vector A, and I can move it anywhere I want. And if I want to add it to vector B, what I do is I do that tip to tail method that we talked about. Now notice that vector A starts here, and it takes me along this path and ends here. And that's where vector B started, and it took me along this path and ends here. So the resultant vector, my final vector, my resulting vector, I'll do in purple here, starts where A started and it ends where B ended. Now, we're going to use this idea of vectors to solve some word problems in which we're moving a certain amount, so that's the magnitude, and we're going in a certain direction. And this really lends itself to the idea of vectors. So here's a problem here. It's a good idea to pause the video, maybe copy down a picture that you think works, and then unpause the video and see how you did. Okay, welcome back. Hopefully you realize that this boat is leaving the port, and we're always going to start at the origin. Notice how the compass rose matches the x and y axis, so I'm going to talk about the origin. So we're going to leave the origin here, and we're going to go for 80 miles in a direction that's 50 degrees north of due east. So, you know, a good way to think about this is imagine going due east this way, and then you're pushing that vector up north. North is up 50 degrees, and that would be 50 degrees north of due east. So if we were going to draw a picture and label it the way I asked you to do here, we would end up with this picture here. The vector length is 80. The angle right here is 50 degrees. And then I asked you to go a little bit further and find the vertical and horizontal components. So the vertical components of this vector would be this, and I'm going to call it y because it matches the y movements up and down. And the horizontal component would be here, and that's x. And again, I called it x because it matches the x movements, the side to side. And this naturally forms a right triangle. And since it's a right triangle, we can use some basic trig. To find the x value, we would use cosine. And I'm going to make a statement, and I really need you to hear and listen to this statement, because this is the crux of this entire unit. And that statement is, once again, we see how the x value is related to the cosine. Remember in the unit circle, when we talk about our coordinates, that the x coordinate in the unit circle represents the cosine, the y coordinate represents the sine, and we see that same relationship come out with vectors. So you can solve this. You have all the skills you need to solve this for x. You could set up a similar trig ratio for y, and you could solve it for y. Just make sure your calculator is in degrees mode. Now that was kind of a nice little example. I'm going to give you another one here. Again, why don't you pause this, see if you can draw the situation, and see if you can answer my question. Hey, welcome back. Hopefully you paused it and you drew it. We have this airplane flying due west at a velocity of 100 meters per second. So we can use vectors to represent distance, but also speed. Or if you give speed a direction, it's called velocity. So we're going due west with our airplane, 100 meters per second. Now the wind is blowing out of the south, so it's blowing north, it's blowing up at 5 meters per second. And if you look at this, this may not be the best way for me to draw this, because the wind is going to be blowing the airplane up north a little bit. And so if I want to find the resultant vector of this, it might be a good idea to tip to tail these two vectors. I'm going to draw in this 100 for the plane and then the cloud or the wind pushes it up 5. And if I tip to tail those two vectors like that, I can end up getting my resultant vector going right there. And now I can solve for what? The magnitude and direction of the resulting vector. So we can find this value r right here. I should call that r. Maybe I'll grab my pen and write r. We can find that r by using the Pythagorean theorem. So we end up getting r is about 11.18 meters per second. Now, that's the magnitude. We can find the angle, and the angle right here, this angle right here, I'll call it alpha. It's the Greek letter alpha. We like to use Greek letters for angles. We could find by using what? Well, this is a right triangle, so I'm going to use tangent. The tangent of alpha is 5/100, which means alpha is about 2.86 degrees. And I said north of west because notice we're in quadrant 2. If we face due west, we had to push it up 2.86 degrees. Now those were two very basic problems, and this would be a good time to play around with your homework that you have and do the front page of the homework. And when you finish the front page, come now to the next slide, and the next slide will show you how to work a couple problems that are more fun than what you have on the front page. So pause the video, try the front page. Hey, welcome back. Hopefully you paused the video, you did the front page. Now let's take a look at a new problem. So pause the video. As a matter of fact, this would be a good one for you to even copy down. Copy this down and then come back and let's talk it out. All right, so let's see what we have. First of all, we have this first set of data in blue here. I'm going to underline it in blue. We are traveling for 60 miles at 100 degrees north of east. So if we face due east and we push 100 degrees, what quadrant does that put us in? I hope you said quadrant 2. That would be right about there. We have this 100-degree angle which goes right here from due east all the way to there, and we know that we're traveling 60 miles out. Now we have a second measurement, and from where that plane is, where this vector ends, the head of the vector, it turned and flew this, 50 miles at 20 degrees north of west. Now what I'm going to do to represent this vector is this picture here. And what this picture represents, these gray dotted lines are the north, south, west, and east axes. And coming off west and pushing up 20 degrees north, I have this new vector. And by situating it here, notice I'm tip-to-tailing these vectors. You know, this other vector is down here, but the best place to put it would be right there. Now that they're tip-to-tailed, I can sketch in the resulting vector r. And one thing I have to do is find that distance r. And then I have to find out what angle is it from where we started. So first things first, I'm going to grab this triangle here and I'm going to copy that triangle over here. But what I actually want to do first is I want to find this angle measurement between the orange and the blue. And that angle measurement's a little bit tricky. First of all, does everybody realize that this dotted line right here is parallel to this, I'm going to call it x-axis, that these are parallel. And if this angle right here is 100 degrees, what's this angle right there? That angle going from the blue line to the black horizontal line. Well, there's a special name for those angles, and I hope you remembered they're called alternate interior angles. So that makes this 100 degrees. Now remember, that's not the degree measurement from the blue line to the orange line. That's only from the blue line to the black line. And if we go from the black line to the orange line, that's an extra 20. So I'm going to argue that we have this picture here. We know this is 60 degrees. This is, or 60 miles. We know this is 50 miles. We need to find r, and we know that that's 120. So why don't we find r? Well, this is not a right triangle, so regular sine, cosine, and tangent aren't going to work. But we do have other tricks up our sleeve, like the law of cosines. So good time to pause the video, use the law of cosines, make sure you're in degrees mode, and get the answer. Hey, welcome back. I hope you got r is 95.3939 ... miles. So down here, we know that the plane is currently 95.39 miles away from its starting point. Now we just have to find the angle of that plane from the starting point. So this 95.3939 ... can go up here into my triangle for r. And now, let's see, I can find this angle alpha, which is right there. That's alpha. In that triangle, knowing that this is alpha, knowing these three sides and that angle, I can switch to the law of sines. And I can find alpha. Good time to pause. Use your trig skills. Find alpha. Hopefully you found alpha to be about 27 degrees. So if alpha is 27 degrees right here, I can come over here and put that angle right there. I can put that angle alpha right in there. So how can we talk about where that green line is? That green line isn't 100 degrees north of east. It's not 27 degrees north of east. That angle is from here all the way over to there. We could say that that new value r is 127 degrees north of east, because we had to add these two together in this instance. Now, I don't want you to think that we're always going to be adding angles. There might be times you have to subtract. But you also could approach where this angle is by using west. This angle right here is, let's see, it's not 100, it's not 27. I'm going to argue that that angle is 53 degrees, and I'm going to let you figure out why it's 53 degrees. So we could say, instead of 127 degrees north of east, that it's 53 degrees, oops, little typo, north of west. So you've seen me work a couple easy problems, and I asked you to do the front page right after those easy problems. And now to do the challenging problem, let's see if you and your buddy can figure out the back page. Give that a go, and we'll talk later.